Good morning to everyone, and it's great to see so many faces in the room, and also hello to everyone online. I'm Vedhus Hoskere, Assistant Professor at the University of Houston, and I'm very delighted to be here to be delivering this course to all of you today. My first lecture is going to give you an introduction to some of the applications of computer vision for civil infrastructure assessment. And then over the next few days, we're going to be going into more detail into some of these topics. I've tried to structure the course so that even if you don't have a background in computer vision, you can start to gain some expertise. So we will go into some details on how images are modeled, and then how we can use images to do metrology, which is the science of measurements, and then how we can collect images, and then also how can we process images to extract useful information. And then finally, we'll go over some of the trends and current areas of research. In the middle also we'll have several tutorials. So I would highly encourage all of you to have your laptops. For the tutorials, they're mostly going to be Jupyter notebooks. So what I want to do first is to get a sense the students in the class, so that I can try to tailor the message to all of you. So a little bit about the University of Houston, where I'm coming from. So the University of Houston is the third largest university in Texas, and the 19th largest in terms of student body in the US. It's a public university. Our expenditures are about, research expenditures are about $250 million. And we're ranked 38 amongst public engineering graduate programs in the US. We have several faculty that are members of the National Academy of Engineering, 15 to be exact, and within engineering we have 8 departments, and recently also an engineering data science program, which is very popular. I'm going to now give you an introduction about the need for vision-based assessments. Now, civil infrastructure spans large areas, and they are critical assets that serve society. Bridges connect regions that are otherwise not connected. Dams, stop water and can be used to produce hydroelectricity. They can also control inland waterways. Roads connect different parts of the nation, and they are all vital aspects of our society, and so they need to be assessed regularly to ensure that they're properly functioning. Now, given the massive scale of these assets, traditionally the only way to conduct assessments at scale for all types of structures is through manual visual assessments. So the way it's been done is you have a person trying to get to a spot where they can see the surface of the asset, and then use the information they're gaining from what they're looking at to make decisions and to document the current state of that asset. So this is the Hoover Dam and the bypass bridge in front of it, and this is an inspection from about 4 or 5 years ago, conducted by the Nevada Department of Transportation, and you can see how much difficulty the Department of Transportation goes through to try to make these assessments. So here we have this inspector. He's rappelling down this column, right? It's a highly hazardous thing to do, just to inspect for signs of damage. Now in the US, visual inspections like this have to be done for every single bridge every 2 years. And there are variations of that throughout the world. But in general, there are periodic inspections that are required of every single asset. Now this varies for buildings and varies for dams and bridges. In Texas, for example, we have 55,000 bridges, which is twice more than any other state in the US. And so it's a humongous task to get all of these inspected, because despite these inspections, we still see accidents that happen. Right? There are things that can go unnoticed, and we still see failures of these assets. And so we need to do our best to try to prevent that. And so visual assessment is the way that we've been able to do this at scale. Of course, there are other methods that are vital when you're doing more detailed assessments of individual parts. But again, if you have to do it at scale for all the infrastructure that is available, vision based inspections and manual ones are the most prevalent form. So the problem is, though, that when you're trying to capture everything so that you can make your best decision, this becomes very difficult. Even if you're doing it through visual approaches, if you have a large network of structures and you want to sort of quantify the extent of degradation, then having a person go out and do all of this manually is still very challenging. Another challenge is that a lot of civil infrastructure is inaccessible, and so having a person go out there and do this is difficult. And then also you have situations after disasters where there could be a large number of structures severely damaged in a short span of time, and to get the city back up and running, you need to quickly assess infrastructure and then make decisions on the safety. So this is a drone video that I took back in 2017 after the earthquake in Mexico City. So there you had a big earthquake, 7.1 magnitude, hitting a densely populated city, and that caused over 10,000 buildings to show some signs of damage. And it took about 3 weeks just to do an initial inspection of these buildings, and then detailed inspections took several months after. And so it slows down the economy, it slows down people's activity, and so if you have to have resilient cities, you have to be able to quickly assess these infrastructure assets. So how do we leverage the capabilities that modern technology is offering in order to improve our productivity with these inspections, improve our capabilities, and allow for more resilient cities? Now, biologically, vision is actually an incredible feat of intelligence. And one indicator of this is the fact that in a macaque brain, 50% of the brain is devoted to the visual cortex. So all of the light that is going through the eyes onto the retina and being processed through electrical signals by the brain, 50% of the brain is processing this information that's coming, and that shows you how much importance evolution has put on being able to assess the world around us, because it's integral to everything that we do, right? So if you look at this image here, um, it's a black and white image, right? And you can see that there's a bridge here, but you can also tell that this bridge is probably over a water body, right? You can't really see the color, but just by looking at the context, the types of piers here, you can tell that it's over a water body. You can tell that there's, pavement or a road here in front. You can tell that those are transmission lines. So there's a lot that you can infer about this scene from this image, despite the fact that it's black and white. And the reason you're able to do that is because you have huge amount of priors, right? You have huge amount of experience as a human in this world looking at things, and you are able to understand the context in which things occur. As civil engineers also you have expertise, and all of that together you can tell a lot about what is happening in this scene. Now this picture, as is represented here, is a collection of pixels, right? And if it's black and white, then it's simply a collection of intensity values. Here it's a matrix where each pixel has one intensity value, which could be an integer or a floating point depending on how much resolution you want to have for your pixels. But it essentially looks like this. It's a bunch of numbers. So this is what a computer sees. And the goal of computer vision is to extract useful information from these pixels that can enable various applications. And so our goal here is to look at different approaches that can allow us to take the images that are now so easy to collect, but then process them and get some useful information out of that. Now, computer vision has progressed very rapidly and has been a leading area for advances in artificial intelligence for several decades. Many of the top minds have worked on solving some of the biggest challenges in computer vision. And here I just have 6 examples of some very common applications of computer vision to get an idea of what this field spans. So the first one is structure for motion. So this is from a paper called Building Rome in a Day. And what the authors did was that they collected a large number of publicly available images of different parts of Rome, and they used that to reconstruct 3D geometries of iconic structures. And that is one main application of computer vision. Some of you are working on metrology and photogrammetry. With computer vision, you get multiple, you can collect images that span multiple views of anything, and you can use that to triangulate a 3D representation of whatever you collected images of. And so computer vision is very useful in obtaining geometrical information of assets using images. Another common application that spurred advances in computer vision was face detection. Now, face detection was around long before modern AI systems, and it was a main problem that people were studying because there are some features of faces that allow special handcrafted techniques to work really well. And so even if you think back 20 years, maybe some of you were not even around then, but we had digital cameras that had face identification. So now, of course, this can be done at scale. There are several social media companies that specialize in being able to do this and group things together. Also for surveillance, it's a big yes, yes, yes. Yeah. So it's a very good question. You have a 2D image. How do you construct a 3D representation from those 2D images? So we're going to go into great detail about that. But to give you an answer in one line, you have a 3D point, right? And that has x, y, z coordinates. If you have an image, you have for the same 3D point, if it's an image, then you can get a u and v coordinate in that image, right? So say you take a picture of this laser pointer. In that image, you can see some pixels corresponding to this laser pointer. But also this laser pointer has a location in 3D space. Now if I take many pictures of this, then I'm going to get many images with some pixels in that image representing this. And there are many unknowns, right? I don't know where the camera was when those images were taken. I don't know the camera model. And also I don't know this location. But if you have enough images, then we'll see that you constrain the problem to find out all of these unknowns. And that's called structure for motion, and we'll go into that in more detail. Today, in a tutorial later on, we'll see how to do it from just one image, making some action. And then tomorrow, we'll see how to do it with multiple images. So face detection, of course, spurred a lot of research. A modern application of that is object detection, where you draw bounding boxes around things of interest, and this can also be used for surveillance, or and is also used heavily in medical imaging to automate the detection of different diseases. Now, another major source for advancing computer vision has come from the self-driving industry. So nowadays we have several companies that can do tens of thousands of miles without intervention from the driver. And you can see the amount of detections that need to be made to enable a system like this. You have, and also there is a hard restriction on the compute speed because all of the detections have to happen in a fraction of a second. Longer to perceive the environment, then there's going to be an accident. But we have companies like Waymo and Tesla doing this at scale. And the key enabler of this is the fact that it's now possible to build robust vision systems that can reliably perceive the environment. And once you're able to do that and construct a reliable map of your surroundings in real time, then you can start navigating through that environment and enable all sorts of applications. Another modern application is in generative AI and search. Here you can see a system, Google Lens, which does many different things. That you have this picture, and there's a sign, and that sign is being translated. So what goes underneath the hood here is an augmented reality system where you have a camera, image is acquired, the image is processed, identify text, and then the text language is detected, and then the AI system doing the translation, and then the translated text is superimposed onto the original image, and then the background in the original image is modified to make the new superimposed text seem like it was there, right? Because it's figuring out that the sign is exactly there, and it's inpainting over the previous text that was there. So it's not only understanding what is in the scene, but it's also being able to modify the scene. Right? So computer vision is where you are understanding, and if you are modifying an image, then that's sometimes called computational photography, but also it can be called generative modeling. So of course there are many more applications, and if I start listing them, then we can be here the whole day. But hopefully this gives you a flavor of what people are using computer vision for. And with that, we can look at how computer vision can be applicable to the problems that we are interested in, which is infrastructure assessment. Now, before I move on, are there any questions? Feel free to stop me at any point, right, if you have a question. I'd love to listen to what you guys are thinking. Now, in terms of infrastructure assessment and management, there are, I like to classify the types of information that we can extract with computer vision into 3 categories. Now again, with computer vision, we're making sense of what's out there. And so the first one is geometric information. So we can get things like the geometry of the structure, or the size of certain damage, or the dimensions of components. And then we have condition information. So this gives us the visual condition of the asset. So you could get things like the damage, the presence of certain kinds of damage, presence of certain materials, and also the context. So you can see what components are there, what is the type of structure, and what is their condition. And we can also use computer vision for structural information. Through videos, we can monitor displacements, or if you're doing at a larger scale, then even images, or if we're doing a larger time scale, then even images can be useful. We can also get natural frequencies of structures as they vibrate, and this can be very useful in understanding the behavior. We can also use computer vision to get mechanical properties of structures. So these are some categories of applications, and we look at some examples now. So let's look at geometric information first. Even from a single image, there's a lot that you can tell if you have some sort of reference, right? And today we'll do a tutorial on single image metrology. How can you get information from a single image? But say you knew the size of this window, right? Can you use that information to figure out what is the area of this falling, right? How would you do that? Yeah, from the window you calculate the pixel length. Yeah, so if you know the width of this window and the height of this window, you can calculate how many pixels represent this window, the width and the height. And so you get some sort of scaling, right? Now, what is the complication that makes it not so trivial? It works for planar structures, but here this wall you can treat as a plane, right? But even though this wall is a plane, there's a variation. And why is there a variation? Exactly. Right. So you have one portion of the window is closer to the camera, and the other portion of the window is further away from the camera. And so the scale, even though you know that this is 3 feet and this is 3 feet, here there are a different number of pixels, and here there are a different number of pixels that represent that same 3 feet. And so the scale varies. Yes. Yes.
So the pixel point at far length partitions
yes.
not scale to the
yes.
actual length.
Yeah. So it's just something that you need to take into consideration, right? Because the spalling area here will have fewer pixels than the spalling area here, even if they're the same size, right? So you need to take that into account if you have to accurately measure.
Because if you look at the left side, then you can clearly see that
Yes.
the farthest window has smaller
Yes.
pixel size. And here the damage area has larger pixel
Yeah.
size.
Exactly. So it's a good point. You can see that, of course, these windows look much smaller. This one and this one look almost the same size, but of course this is much smaller because it's closer. So the image is a projection of the real world to a 2D plane, which is the image plane. And that projection causes a perspective distortion. And that's something you need to take into account if you are trying to measure things using the image. Okay. One way to take into account that is to make sure that when you're taking the image and you want to measure something, you set it up so that it's straightforward, right? If you keep your image plane exactly parallel to the plane where you're trying to make a measurement, then that will simplify your work. But sometimes that's not possible. And so you end up with situations like this, and then you have to properly account for the variations.
So can identify that the object is far and size is probably same. When you see a computer which is storing the intensity, probably the intensity values are also approximately same. How does the computer identify that it's a 3D kind of thing happening here?
So the question is, how does the computer understand the perspective in this image? It's a very general question. You can build AI systems that can understand the perspective, right? You can. The method we look at today is a partially manual method, where the human or the user will identify parallel lines, and then we can use that to orient a world coordinate system. And these parallel lines intersect, because parallel lines in the real world will not intersect. But in this perspective transformation, the parallel lines will intersect at points that are called vanishing points. And once you have the vanishing points, then you can do some computation to be able to calibrate a camera and figure out that projection model. We'll go into more detail just after lunch. But so what I described is a manual process, but also you can have a deep learning or AI system that automatically identifies those parallel lines, and you would train that by giving it many examples, and then it learns to detect patterns in what that is. Or you can use more traditional image processing techniques where people have built filters that can detect lines, and then you can use that together with some rules to build an automated system. So there are many ways to solve that problem. But what's important for us to understand is the fundamentals of how the camera model works and how we can use that to do our metrology, which is to make our measurements. And then we can think of how to automate that as well. Other questions? Now, so we can do that from a single image. We can also measure things like defects, right? So say we know what the height of this lock gate is, then there are some cracks you can see there, right? And you can use that information about the height of the gate and the perspectives that I mentioned to try to assess the length of these defects and also the sizes of these defects. But one challenge that occurs is that sometimes it's hard to tell whether something is a defect or if it's just a feature of the structure, right? So one way we can address this is by having a lot of examples of what is a defect and what is not a defect. And that's pretty much how all of the self-driving technology works. You have a huge number of examples where you're collecting, and you're collecting all the time. You're continuously growing your data set. You're continuously chasing edge cases. So it's a never-ending process. But still, you can hit the 99%, and then as you chase the 0.99999, that becomes a never-ending process. But still, with the 99%, you can get a lot done, and we'll look at some methods that can help with that. Now, if you have multiple images, then you can use constrain how you are setting up your measurement problem, and you can construct the geometry of the asset and use that constructed geometry to make measurements. So here you can see examples of different structures that we've inspected over the past few years. That same building that was damaged after the earthquake in Mexico City in 2017. You can see a 3D model that we built. This is one that we built of a bridge in downtown Houston a few years ago. And this is it's a large bridge. There's a Buffalo Bayou here. It took us a whole day to collect images for this bridge. Right? Here are some tainter gates for the Ohio River in the tri-state between West Virginia, Ohio, and Kentucky. This is it's a truss bridge. This was done using LiDAR, which is also another way to collect visual information. And this last one is our stadium on campus that we inspected using aerial surveys. So tomorrow we'll do some data collection activities with the drone. I haven't spoken to Jothi, so I don't know exactly what we're going to be doing, but I think he mentioned something about a bridge. So we will study. I'll talk about how to set up your data collection strategy, because there are many things that you need to account for. Right? If you're looking for defects, then you need resolution very close to the structure. But also, if you're looking for geometry, then you need to be far enough so that you can identify parts of the structure that are the same. Because if you're very close, right, if I'm very close to this board, then everything looks white. Right? If there's a crack, I can probably see it, but I can't really tell which part of the board I'm looking at. Unless I come far away, then I can see where the board intersects with these switches and with the screen and the edge of the wall, and then I can put it into context. Right? So there's a trade-off with the scale at which you're collecting data, and we'll talk about how to decide what is the best scale for your particular problem. That's more views of that 3D reconstruction of that building. Now, of course, once you do this, you get a 3D mesh, and then you can use that to make all sorts of measurements. Right? So this is once you have this, it's much easier to do this than to go out and make these measurements. If I had to measure the width of the bridge from here, this is sort of inaccessible because there's a river here. Right? I can measure it from the other side, but if I had to measure some defects there, that wouldn't be possible. But once you have this representation, then you can make those measurements. And to collect these images, of course, we use drones. I didn't talk about that, but we'll talk about that more as we move on. Okay. So we can use computer vision to get you had a question there? We can use computer vision to get geometric information. We can also use it to get condition information. Now, once you take a picture, provided it has sufficient resolution, then visually you have captured information. And if you take a picture of a defect, then in the is stored some information about the defect, and you can visually see that. So that itself is very useful. And these days, with a lot of usage of drones, because they enable easy access to defects. Part of the process is where drone images are collected, and then you have a person looking at those images to see what is happening. Now, the problem becomes that if you have too many images, then it's very hard to look through all of them. And it's very mentally exhausting to do that. And so deep learning and artificial intelligence gives us one means to automate the identification so that when you have many images, these images can be processed through your AI system. The AI system identifies which ones have damage. And then you can do further processing on those, or you can quantify those. It becomes useful to filter out content. The basic way this works, and I'll illustrate it with a classification problem, is that you have some sort of model, which is a series of computations, and you have a data set of manual annotations of examples of damage and no damage. And then each image has this annotation, whether it's damage or not. So you create this data set, and then you show it to your model. And the model is able to learn what the model needs to be in order for it to be able to make the same classification. Okay. So we'll get into more detail about how this works later on. But essentially, you're creating a training data set, and you're showing this training data set to a model. The model updates what are called parameters. So parameters are basically knobs. Right? You can think of them as knobs that are being tuned in order for this model to output your desired result. And in this case, my desired result is that if the model sees an image of something that is damaged, then it should say there is damage in that image. And if it sees an image where there is no damage, then it should say no damage. We can represent these categories as integers. So maybe I will call it as 1 and no damage as 0. And so then the model's job is just to output 1 or 0. And you can think of the model as a function, right? So it's a function. What's the input to the function? What's the input to the function? An image, right? And the output is 0 or 1. So it's essentially a curve fit. That you're fitting a curve from the image space to the space of 0 and 1, so that damaged images map to 1 and undamaged images map to 0. Deep learning is one way to enable this. It's the science of how to tune those knobs so that you can fit that curve. Essentially, AI is also the same thing, right? You have huge amount of data, and you are fitting a billion parameter curve to that. There's much more to it than that, but to explain it in one sentence, that's what I would say. Another thing that computer vision can be very useful for is to help identify damage that's not apparent directly to the naked eye, because you can have cameras that can capture spectrums beyond the visible spectrum. One type of data that we use a lot is infrared. So infrared can map electromagnetic radiations from the infrared spectrum. So if there's heat, that generates infrared radiation, and that can be potentially useful. So here is an example of a picture of a bridge from our drone, and here is also a thermal image of the same part. Now from this image, you can tell that there is a crack, right? But what you can't directly tell is if that crack has become a delamination, which means it's going to chip off soon, or is it just a crack? Okay, that's harder to tell. But if you look at this image, thermal image, what can you see here? You can clearly see that there's a separate piece there, right? Because the temperature of that is different from the temperature of the rest of the structure. So here, this is illuminated really well because the sun is shining directly on it. And so that's one constraint, is that you need good illumination sometimes to make it very clear, but that's true for even for vision, you need light. But here you can tell that there's a delamination and that's chipping off. Now here is a deck. It's a steel deck on a ship. And here there are two halogen lights, and so we're using the halogen lights as a heat source to heat up the surface. But here you can't really see any corrosion, right? But in the thermal response, you can clearly see that there's a patch in the middle. And when we scrape off the coating, lo and behold, there's corrosion underneath. So if you have a heat source, then you can also use computer vision to detect damage that is hidden otherwise. For things like delamination, for corrosion, undercoatings, it can be very useful. Now, here we see that there is a clear signal, which means there is a clear change in intensity when we have that hidden defect. Also, for visible defects, there's a clear change in signal because the intensity, the crack intensity is zero almost. It's black, and the surrounding intensity is much higher. So there's a clear change in signal, but then how do we automatically identify those signals? And that's where, again, deep learning becomes useful. We can recap the process that I spoke about, but instead of just classifying images, we can also classify pixels, and we can get that information at a pixel level. So the way it would work is you develop annotated data sets. That's the first step. And that means you need to know what defects it is that you are looking for. Because if you have to annotate something, then you need to have a list of things that you're looking for. And then you annotate those things in your images. Now, what kind of annotation do you need to do? That depends on what kind of output you want. If you want a classification where each image is classified, then you simply classify each image. But if you want the exact pixels that correspond to spalling, you can barely see it, but you can see that it's, you can see some blue patches there and some gray patches. If you want the pixels that correspond to the defect, then you need to annotate each of those pixels in your data set generation as well. And then we can use drones or robots or even handheld cameras to collect data. If you want to automate it, then you can have some routine on your drone or robot to collect images. And then with the data that you've annotated, you need to show that to a deep learning or AI model, and you train it. You tune those knobs, and then it learns how to distinguish crack pixels from background pixels, from spalling pixels. And then you can deploy that model on the new images that you get. And there are different kinds of information that you can train models for. For example, you can identify damage, material, or components. Now, why would you? It's clear why you would want to identify damage, right? Because this is a cause of concern. You want to see which images represent that. But why would you want to, for example, identify structural components? Right. Yeah, exactly. You want to know the context in which the damage is occurring. Because if you have a window that's cracked, that is probably not of as much concern as if you have load-bearing column that's cracked. Right? So the context in which the damage occurs is very important for you to be able to make an assessment about the integrity of the structure, as well as what course of action needs to be taken subsequent. And so that's why we need to extract as much information as possible. Now, when we are doing this, we are understanding the semantics of the image. And so if you segment different classes, right? So here you can see the materials, so steel and concrete, they're segmented in different colors. and you can see some corrosion in red, spalling in blue, and the rebar in orange. You can see segments of each of these classes. And because you are identifying the semantics and segmenting out these different classes, this process is called semantic segmentation. And with deep learning, you can automate the process of semantic segmentation to process these images and identify these semantics automatically. Now, once you've done this for one image, you can do it for all the images that you acquire from your drone survey. And then you can put that together into a 3D reconstruction using photogrammetry. You can also then use that photogrammetry as a basis to create digital twins. But you can get more information from the image. All of the semantic condition information from the image and superimpose back onto your 3D reconstruction. And that allows you to have this searchable representation of your asset that is phenomenally useful for making decisions, for persisting your persisting snapshot of the structure in time. So when you make more assessments in the future, you can compare against that snapshot that you have. And you can do it intelligently because you have all of these semantics that have been extracted. So rather than doing it manually, you can, it makes you much more productive when you're working in that space. And you can use that also to categorize different components into different severity categories, and so on and so forth. So that's the summary. We can look at one example. So this is that building that I showed you. That's me, and this is a colleague of mine from University of Illinois, and this is the late Professor Manuel Ruiz Sandoval from Mexico City. So we visited Mexico City after the earthquake 2017. You can see our drone there. So this building was severely damaged, and it was in fact very, very scary even to go close to that, because you can see it's like compromised. But for buildings like this, oftentimes you don't need inspections because you need to tear it down. But still, it was a good test case because we can fly the drone around it and identify different types of damage and measure them and so on and so forth. So we collected this drone survey. But even though this was an extreme case, it's still the technologies that we tested here are still applicable for more routine cases as well, which are much more common. Now, to collect this information, we planned an automated drone flight. Now, at the time, there were beyond visual line of sight restrictions, which means that the drone cannot fly beyond visual line of sight. This is a common restriction that is in place in many countries. You can get a waiver these days in the US for specific kinds of inspections. But at that time, we had this waiver. And so, since I'm standing here, the only parts of the building I can see is this face and that face. And so, also with the drone, I can only do those two faces. I can do a little bit of this face as well by moving the drone further away. But there's a road there with some traffic, and we had limitations in how much we could fly. So we restricted the flight path to this area. And this illustrates some of the challenges that are typically faced when you deploy drones in urban areas. Right? In rural areas, it's not so much a problem. But in urban areas where there's dense collocations of infrastructure, there are many challenges when you're trying to deploy UAVs. And so part of that will be solved, I think, through practices and technology, but a lot of it has to come down to regulation and coordination as well. But in any case, in 2017, this is the path that we chose. This was with a DJI drone, and we used a software called Litchi, which is just a $25 app you can buy on the Play Store. These balloons in purple, those are points, those are keyframes for where the drone needs to go. And for each of the points where the drone needs to go, there's a point where the drone needs to look. So the drone has a gimbal with a camera, and the gimbal controls where the camera is looking. So for each purple balloon, there's a corresponding blue balloon. And so those two together define the location of the drone and the location where the gimbal needs to be looking. Now, there are many challenges here. You need to avoid obstacles. These days, you get drones which have reasonably good obstacle avoidance. But back in 2017, that was not the case. You need to make sure you're covering the structure, right? So when you plan how many paths you're taking, you need to calculate so that based on how far you are from the structure, you need to calculate what is the height difference between the successive paths. Also, there's usually GPS error, and so you need to do some tests to see what the GPS error is, and calculate whether there's a chance that you might hit an obstacle. So all of that is something that needs to be taken into account, and then you can deploy that. So here is another building. So here, it was not as bad, and I could move from here to there, and so I could see the drone as it was flying. This is sped up, but you can see the drone going around the building. Right? And so this is purely GPS based, and there's no obstacle avoidance. It's just flying based on our manual planning, based on our understanding of the obstacles that were present. And then once you have that, you can also, if you have a deep learning model that's trained, so here we had a model that we had trained on other data, and then we deployed it on this. And on the front, you can see there's not too much damage, but on the side, once it starts showing, you can see that it starts to detect much of the damage. Now, this model is not perfect because it wasn't trained on this structure or these kinds of structures, but it still illustrates the concept of how you can identify. And the identification is switched on and off just to show you what's behind it as well. Now we can superimpose different models that identify different things. So here we have a model identifying the components and a model identifying damage. And you can superimpose all of that to build a semantically rich representation of your assets that have been semantically segmented to identify damage and context. And then you can put it together in this through this 3D representation. And now these 3D representations are, today paving or are serving as the basis for creating digital twins, because they have huge amount of condition information, they have the geometric information, so all of that can be used to produce a digital twin. This course is not about digital twins, so I won't go too much into that. I'll talk a little bit about it on Friday, but again, computer vision can be very useful in enabling this. So using, and I call them smart digital twins because again, you have the semantic information automatically identified, and so they can function autonomously. Okay, so we spoke about geometric information, condition information. The last thing we'll talk about is structural information. Now, there are different kinds of structural information that you can extract using computer vision. And these include, but are not limited to, displacements, natural frequencies, mode shapes, material properties, and so on and so forth. Anything that is visual cues, you can potentially measure. So I'll show you a lab experiment that I did many years ago at the University of Illinois. That's a shake table at the bottom. This plot is not very clear. I don't know why. But you can see the structure that's being that's on top of the shake table and it's vibrating. And you can see yellow boxes around each of these stories. What I've done here is using a DSLR on a tripod, I've just taken a video of the structure that's vibrating. And I tried my best to keep camera plane parallel to the plane of the structure. It's more or less a planar structure, so that's not too hard to do. And then I drew these yellow boxes manually. Regions of interest. And then I'm using an optical flow algorithm, something that we'll study later on in this course, to track the locations of constant intensity. Because here you can see these bolts that are holding the masses to the floor plates. Those bolts are rigid bodies, or we can treat them as rigid bodies for the purpose of our study because the structure itself is quite flexible. And so we can track the rigid body because that rigid body nominally has the same intensity, right? Compared to the background, there's this rigid body that has the same intensity that's moving. And so if we track pixels of constant intensity within the region of interest, like from frame to frame, then we can find where this object is at any given point in time. And if I get the pixel locations of each of these stories, right, each of the stories I can treat as a rigid body, I can average the locations for each story. And then here I'm plotting the location as a function of time. Now you'll notice here that the unit that I'm plotting is barely visible. I'm sorry about that. But it's in millimeters. And that's because since I have my plane of the structure parallel to my image plane, I need a single scaling factor, and I can obtain my displacements in real world units. Okay? So if you set up your camera properly, then you can simplify your work later on. We'll look in more detail about how you might do this, and you guys will get to experience it yourself. But once you've extracted these displacements, then you can do all sorts of things that you would do, or that people have studied in structural health monitoring and modal analysis. For example, you can obtain the mode shapes, right? So this gives you valuable information about the dynamics of the structure. You can see the blue line, that's from the camera, from my DSLR measuring at 60 frames per second, 60 hertz. And then we also have an accelerometer, which is sampled at 64 hertz, which is the gold standard for these sorts of vibration problems. And you can see that the mode shapes from the accelerations and those from the camera are almost identical, which means that we're able to get all that information. It's important. Why is this sampling rate important? I don't know if that's something that everybody's familiar with. But sampling rate has to be more than twice your highest natural frequency. So here we have 14.13 hertz. So we need at least 30 hertz if you have to measure all of these modes. So 60 hertz, you can measure all of them. But another thing you can do with videos, right? So of course this is a video here, is you can directly band pass these videos. Yeah.
Taking the mode shapes
Yes.
for vision.
Yes.
So it's a combination of all these mode shapes. So you're identifying each mode shape from the displacement.
So I have 6 displacements, right? 1 at each story. So it's like a signal. And then I'm using the eigen realization, the ERA method, next ERA method, because here I have a broadband white noise excitation. So I'm using the next ERA method to compute the mode shapes. I talk about that because that's not a vision specific method that can be applied to acceleration. It can be applied to velocity also. But essentially, you're getting this displacement signal here. Now it's clearer, right? I think when I played it, maybe I compressed it. That's why. But you're getting the signal, this displacement signal, and you can use that for any sort of processing. But what the camera is useful for is getting that signal, right? So even if it's a static displacement, you can measure, which is otherwise pretty hard to measure. Yes. So you can use the extracted information can be useful for getting dynamic properties, and it can be very accurate. Now another thing you can do is something called motion magnification. So this was proposed by Bill Freeman's group from MIT back in the 2012s, 2013s. So here what they do is it's a combination of computational photography and computer vision. You're band passing the video at different, identify the natural frequencies, and then you band pass at the different frequencies, and then you reassemble the band passed responses into the video, and then you can see the structure vibrating at different modes. So that you can see the first mode here, it's all moving in the same direction. And then this is the second mode. You can see that there is a point that's not moving here in the middle, approximately. So these methods they're good for visualization. There have been some advances here that make them more accurate, and one advantage of this sort of method is that you can get a full field mode shape. In the previous case, I have a discrete mode shape. Right? I have measurements at the floor points because those are the boxes that I selected. But here you can get something called a full field measurement of the displacement at different frequencies, and then you can reconstruct that into the overall displacement. It has many applications when you're looking at dynamics. There's been a lot of research on this, especially from Michigan Tech and from Rice University. And I can share those details if you're interested. Now we can do this also in the field, and also if there's not enough light, you can use your own light source to do this. This was a campaign done by my colleagues at the University of Illinois, Fernando Gomez and Chung-Chul Yoon. They were working on a project with the railroad, and they had to measure the displacement of this truss bridge when the train was going over the tracks. The problem was that the train was only passing at nighttime because it was on a schedule and it only passed at that time. So the solution was to get our own light sources. And so they took these stands and they illuminated this point on the bridge. And you can see a video here. You can see the points that are being tracked. And you can see the measurement as well as a simulation with the FE model of the bridge. You can see that they match up sort of reasonably. This was a field demonstration to show that you can do these sorts of measurements even in the most challenging conditions. Now, one problem is that in these sorts of situations, it's difficult to span the whole bridge. So there's a specific point you want to measure, then you can do that. But if you want to get the whole bridge, then it's harder. And so one thing that I had looked at in the past was to try to use a divide and conquer approach where you do parts of the structure one part at a time, and then you combine the signals from that. And you can do this both the still camera, but also you can use things like drones, right? Because the drones can navigate by itself and collect that information. So here is an example. Now, of course, when you're using drones, there are some challenges. So here we have a camera, coordinate system, and we have this drone. Now, imagine both of these are measuring this structure with a video. And if the drone is still, then both of these, the camera and the drone, will essentially produce the same signal, right? You can see the drone signal, the camera signal, they're the same. But once the drone starts flying, right? Once the drone starts flying, then because the drone is moving, the drone is not perfectly still, that creates some variation because the camera is moving. And so the question I had was, can you get rid of that extra noise from the drone's motion and recover the original signal, or at least some parts of it that are useful? So we did some tests in the lab to investigate this. You can see this phantom, the same phantom that we used in Mexico City. It's flying, it's collecting images, or collecting a video. You can see the video here, and you can see we have some markers installed to make it simpler. So when you have these markers, they're called Aruco markers, similar to, well, they're kind of like QR codes, which are immediately identifiable. And so you can see the drone video, all of these are identified and these are tracked. And if I plot the frequency content of the signals that are extracted here, you can see that with drone signal, there's a large amount of power intensity in the very low frequency spectrum, right? Part, there's a lot of power versus in the blue line, it's zero there, or it's close to low power. And so what we realize is that because the drone hovering frequency is lower than the structure vibration frequency, we can filter out all of that using a bandpass filter. And we obtain just the information about the structure vibration attribute. And so even with the UAV signal, we're able to reconstruct 4 more chips. So I think that had a 24 hertz camera, so we couldn't do the last 2 more chips, but you can still get the others. And you can see that these are the MAC modal assurance criteria, which measures the distance between the mode chips, and you can see that the camera, the ground camera panning as well as the UAV panning, they're very close to each other. So the UAV provides, in this case, also a useful tool to acquire information from different parts of the structure. We also tested this on a pedestrian bridge. This was over Woods Lake in Mahomet in Illinois. And that's the bridge over there. You can see it's sort of a small suspension bridge. That's the details of that bridge. And here is the drone. We put some markers there to make our lives easier. But you can do it even without markers because there are usually natural features that are constant intensity as the bridge is. You can see the bridge vibrating a little bit. I had my colleagues jump on the bridge to cause that to shake. But that's a video from the bridge. And you can see that the drone is hovering and there is some motion, but you could tell when the bridge vibrated there a little bit. And that's the signal we're looking to extract. This is from the finite element model, and this is from the drone, from the UAV, which is the unmanned aerial vehicle. I don't know if I said that. And then accelerometer. We only did it for half of the bridge, but you can see there's a reasonable match. It was much harder to do it for this real pedestrian bridge, and mainly because you can see that the second mode is the first mode we couldn't get because it was very close to 0.5 hertz, which is the UAV hovering frequency. Second mode we were able to get, but there's some, it's not perfect, right? And then we got the other modes as well. There's some, it's not perfect, but we're able to recover the signal, right? So people have worked on this since we proposed this back in 2017, and have come up with some ways to address some of these issues as well. Okay, that brings me to the end of this introduction. In summary, computer vision can be used to extract geometric condition and structural information towards improving infrastructure assessment. It enables measurement and reconstruction. With deep learning, you can use that to automatically detect and document damage. Hidden damage can be made visible through infrared for some types of damage. The camera is also a very robust and versatile vibration sensor, right? And they can be used to accurately measure displacements. And UAVs provide more data acquisition options, both for geometry, for extracting condition information, and also for measuring displacements. There are rules for how the drone should operate. As you rightly pointed out, there's this inherent trade-off, because for identifying defects you need very high resolution, but to identify the geometry you need some optimal resolution. So if you get very close, then it's very difficult to identify geometry, and that is a trade-off that you have to deal with. But those are not the only two constraints. There are many other constraints, which is that you cannot get too close to the structure with an autonomous robot, or even with a manual one, because there's the risk of collision. And also there are restrictions, there are legal restrictions, because if you're flying in airspace, then you have to make sure you're not colliding into planes. Also, you need to make sure it's not going to fall on somebody's head. And because of that, at least in the US, the FAA has very strict guidelines on how to plan for a flight. And also, if you're doing public assets, then the Department of Transportation also has rules that you need to follow. For example, in Texas, if you're doing a bridge, you must fly at least 50 feet above a bridge if there's traffic on the bridge, because they want to have a factor of safety above the height of the tallest truck that might be on that bridge. And so I'm sure there are similar rules here in India. So there are all of those constraints. Now, there's no fixed answer to your question. It all depends on the specific structure that you're looking at, and very, very importantly, what your objective is when you are collecting the data. Because the objective is going to drive all of your decisions. And so you need to decide first, are you looking for damage? Are you looking to create a 3D model? Or are you looking to measure vibrations? All of those decisions have to be made first. And then you can, looking at all of the legal restrictions and all of the safety restrictions, and you can maximize then your objective of whatever data you're looking to collect. So if you need to be farther away, then you can choose a camera with a longer focal length so you can see further, or you can have a zoom lens or something like that. So there are ways to work around it. But it's a good question, but it's a question you need to answer every time. I'll give you some rules that will help make that decision, but you need to go through that process every time, at least for now. I think that's the... Your other question was about, can you see cracks that are propagating with infrared? Also a good question. For cracks that are deep in concrete, for example, there's not that much of a strong thermal signal that sort of crack might result in at the surface. But that being said, if it's a very big crack, or if there's a hole, say through some water ingress that is making its way through, then that's probably kind of thing that you will be able to see with the thermal camera. Delamination is something that for which is used very often. This includes things like delamination on pavements. From above, you can get really good signals for delamination of pavements. Also, for the example that I showed you, once it gets to that stage, then there's a clear signal. But otherwise, one problem with civil infrastructure is it's difficult to do active thermography. Active thermography is where you provide the heat source, and what that allows for is non-equilibrium heat change, right? Because when you apply the heat source, the rate of change of heat is going to be different, and so you can observe that. But when there is passive thermography, like with the sun, then it reaches an equilibrium state, and so at the equilibrium state there needs to be a difference in temperature that you will be observing. So that is harder for small fine cracks. But yeah, if you can get an active system there, then it makes it a little easier. Yes. Yeah, it's a good question. In general, it depends on, again, what you're trying to do. If you're trying to do photogrammetry, then photogrammetry works. One main step in photogrammetry is matching features of the same object across multiple images. That means ideally you want the same feature to look the same from different images. Now, if you have a very large structure, it'll take you several hours to collect images of that structure. And as the sun moves, the shadows will move, or maybe there's cloud cover that comes and goes. And because of those shadows, a part of the structure that looked a certain way at 9 a.m. is going to look different at 11 a.m. and it's going to look different at 1 p.m. So ideally, for photogrammetry, you want cloudy sky but no rain, so that your drone doesn't get affected. So if you have a cloudy, then that has diffuse shadows, so it's sort of uniform lighting, and that's ideal for photogrammetry. Also for things like identifying cracks, if there's very high dynamic range, which means if there's very bright and very dark, then and if you have a picture of that, it becomes difficult for the camera to adjust to that high dynamic range. So you may have to use HDR high dynamic range, which accounts for that changes in intensity and normalizes, so that you can see things even in the darker portion or see things even in the lighter portion. Right? Those are all practical challenges that you will encounter. So if you can control it, more often than not, you don't have a choice, right? You have to pick a day and then you go out, and then you pick a day hoping with your best guess as to whether or not it'll rain, and then you go out and you make the most of it. But if you can control it, then ideally you want cloud cover without rain, because that gives you uniform lighting for the whole structure. So one question there, and then I'll come to you. Yeah. Yes. If you can accurately measure how much the drone moved, then you can correct for that. Yeah. So people have looked at that, trying to jointly estimate the drone displacement as well as the displacement of the structure. One way to do it is to use points that you know are stationary in the scene. If the point is stationary but it's moving, that means that all of that is because of the drone's motion. Yeah, so you use that to extract the information about the drone displacement, and then you incorporate that into camera metrics. We'll see camera metrics after lunch. which is the camera matrix gives you the location of the camera with respect to the world and the properties of how the camera takes the world coordinates and transforms it into image coordinates. So we'll look at that in more detail. But you can get the displacement of the camera, you incorporate that into your camera matrix, and then you can get the displacement that you're measuring. But the challenge there is sometimes, or most times, it's hard to find a stationary point if you're doing, if you're trying to measure civil infrastructure that's vibrating. Like a bridge, for example, it's usually across something that is hard to cross otherwise. And so if you're trying to measure perpendicular to the bridge, it's usually a highway or a river or bay or something like that. And the stationary objects can be very far. If you're focusing in on a particular point, the stationary object can be very far, and so that is also usually not moving because it's so far. So, but if you do happen to have something that's stationary, then you can recover it. There are other ways to do it is to use deep learning where you disambiguate the signal somehow. But I think it's an active area of research as well. How do you disambiguate that signal? But there are a few papers that have come out, so you can, if you go to, so if you find this paper and you look at the citations, there are a lot of papers that have kind of built on this. So I'm not in touch with what has happened most recently, but a lot of people have worked on it. And then you see what is the drone, because there's going to be a clear cutoff. So you can just measure the frequency from the signal that you have, because like I showed you here, you can see that there's some peak at the left, and then you have your structure frequencies. So you have to remove everything that is associated with that peak on the left. Yeah. But even from the bridge side, it looks similar, except that the first frequency is overlapping with this, right? So you lose that information because you're filtering that out. So that's the cost of this approach. Yeah, so this was not by me. This was by Fernando Gomez and Hyung-Chul Yoon. But they knew the size of these members. That's true. But I don't know exactly what they did here. But at this scale, at this level of magnification of zoom, the variation in the scale from the bottom to the top is going to be small. So if you just average, you'll get a reasonable estimate. But it's true that you're saying because it's on the ground and the bridge is there, so it's not parallel. So I don't know if they how they accounted for it. But if it were me, I would probably, if I knew the bolt dimensions, well, if I know the bolt dimensions, then I can do each bolt separately. But I think they did them all together. And you can average the scale factor here and there, and that should give you a reasonable estimate.
Digital image correlation.
Yes.
Is it a subset of this?
Yeah. So it uses optical flow, which is the same method that's being used here. But with there, instead of using natural patterns, you typically you spray some dots which create that random pattern, and then you can see how those patterns are changing. It's the same principle where you're tracking points of constant intensity across time. There was some question there. Yes. So the question is, can computer vision be used to categorize the damage based on a severity basis? There are a few ways you can do that. One is you can use some computer vision technique to make measurements and then use the measurements to categorize the severity. For example, you have a scale for what different sizes of cracks mean. Then you can use that scale after you measure the crack size to classify the severity. The other way is to have examples of different types of crack. For example, you could have a shear crack or you could have a flexural crack. Maybe those have different implications for the structure. If you have a lot of examples of those in the context in which you want to deploy, then you can create a training set that differentiates between those types of cracks, and then you can deploy that. Now, one thing you need to be careful of is that if you're trying to classify cracks based on severity, that classification depends on the scale, or shouldn't depend on the scale, right? Because if I take a close-up picture of a crack, it's going to look big, versus if I take it from there, it's going to look small. But it's the same crack, so it should have the same categorization. So you have to somehow normalize that, either by resampling, or if you can provide enough context, then maybe a deep learning model can learn that information as well. But if you can measure, you can use also you can use depth cameras to give approximate measurements. Then you can use a measurement to make the classification of the severity. Other questions?